And we continue my video series with reactions of carbonyl compounds. And this will probably have to be split up into 2, hopefully not 3 videos. I'm going to try to get through it as quickly as I can. The basic ones are acyl substitutions, on which you have a carbonyl carbon on which there is a leaving group, and something that is a less good leaving group or equal to less good leaving group, depending on how you Le Chatelier it or swamp it out, attacks the carbonyl carbon and kicks off the leaving group that's already there. So in this case, chlorine is the better leaving group than all of these nucleophiles, and so you just sort of clip it on. A good rule of thumb is bad leaving groups replace good leaving groups. And here you can pause it right now as just a regression of how that works. Number 2 is the Fischer esterification, on which you go from a carboxylic acid to an ester. Basically you add an alcohol and trace acid, but I'm going to go through the mechanism in a little more detail. First step is you protonate the carbonyl oxygen, and that gives it a positive charge. Then the alcohol group attacks, and that has a resonance structure right here, which moves the positive charge down to the carbonyl carbon, and so the alcohol can attack it. Alcohol is not usually a good nucleophile, but it can attack where there's a positive charge. That goes to, this is your alcohol that's already attached, and it has a positive charge there. You have 2 leaving groups on this tetrahedral intermediate, so essentially you're going to swap out the hydrogen, which is the important part, over to water here to make that the leaving group instead of this. Now that you have that, the tetrahedral intermediate collapses, it kicks off the water, and then a base takes away the extra hydrogen that you took on in the first step. Base is probably something like water. And there you are. That's your ester. Note about this is the exact reverse reaction. Notice how these steps are all reversible, is acid catalyzed hydrolysis of an ester. 3, we're going to look at the base catalyzed hydrolysis of an ester. You go from an ester back to an alcohol, but in this case, or back into a carboxylic acid, but in this case you go to the conjugate base of that because it's base catalyzed. If you have a tertiary alkyl group and you do that, as soon as you protonate, this tertiary group over here is a good leaving group because it's a tertiary carbocation. So these electrons pop over and that pops up. So, at the end of the day, you end up with this guy right here, which attacks onto water to get your alcohol, your tertiary alcohol. And, that gets protonated and deprotonated and all that jazz, and you have R double bond OH. This was the OH from the top, and when this bond came over, it formed that thing right there. They're all in the same positions. 5, transesterification, and this is really similar to some stuff we're going to see later, so this is a good one to know. You have an alcohol, and you mix it with an ester, and you get a different ester. What keeps it from going backwards is that you put so much of this in that it swamps it out and drives it toward the products. It's your old friend Le Chatelier. Reactions of carboxylic acids are, the key word there is acid, right? So anything that's basic will just tear off that hydrogen. It's right here. And you'll get a series of salts. NaOH, NH2 connected to any alkyl chain, and OCH3 minus. Good things to do that with. Next thing we're going to look at is acid-catalyzed amide hydrolysis. First step is you protonate that oxygen, you hit it with water, and then you convert the water to a bad leaving group, OH, and the NH2 to a good leaving group, NH3+. And when the tetrahedral intermediate collapses, NH3 kicks off. It oftentimes doesn't stay at NH3 because it's a pretty good base. It steals that hydrogen back that was originally popped onto the top oxygen. So you end up with a carboxylic acid and NH4+. Next thing we're going to look at is a Gabriel synthesis, and the hallmark of this is the phthalimide, or this big old guy right here. When you take that hydrogen off the nitrogen, you leave a negative charge on the nitrogen, which is stable because it can resonate up or down onto either of those oxygens. That'll reach out, any alkyl chain with a halide on it, CH3Br, CH3CH2I, will work. In this case, we're using the latter. It's going to go by the SN2 mechanism, kicks off the iodine. So now you have an alkyl chain on the nitrogen. And from there, it's sort of an acid-catalyzed hydrolysis mechanism. You protonate that, which turns it into a good leaving group. And then when water hits the carbonyl carbon, it causes a tetrahedral intermediate to form and collapse, and it kicks the nitrogen off of half of it. And then you deprotonate it. So now you just have to do that same thing again. You have to protonate the nitrogen a second time, hit it with another water molecule, tetrahedral intermediate forms and collapses, and it kicks off your NH2 completely. Your NH2 will behave a lot like the NH3 did in the thing we just saw, in the sense that it will steal a hydrogen back, and you'll end up with NH3 plus connected to the alkyl chain, and this residue, the dicarboxylic acid. Then you treat it with a little base, and you get your primary amine. You could also probably do a base catalyzed hydrolysis of this. Hydrolysis kind of goes both ways in that you can use acid and base. You can also hydrolyze a nitrile with acid, C triple bond N. And when you do that with acid and heat, it goes to a carboxylic acid. That's a pretty common one. When you have a dicarboxylic acid, you can form 5 and 6 membered rings pretty easily by making the acid anhydride, because it can curl up if it's long enough. See how this guy, when you rewrite it in its curled form, it's really this. And using lasso chemistry, you can see that there's water in there. You can sort of tear that out. Or, one protonates the other, serial protonation, deprotonation. Then the negative charge hits down here, forms collapse, gone. This reaction is catalyzed by heat. You'll also see it catalyzed by acetyl chloride, acetic anhydride, or P2O5. So if you see any of those, that's good to know. This is nucleophilic addition to an aldehyde or a ketone. It's pretty basic. It's a lot like your basic acyl substitutions in the first step, and that you're using a nucleophile, but in the second step you don't have anything that you can eliminate. So the O- just grabs a hydrogen, and you end up with a tertiary alcohol with your nucleophile attached to it. A good example of this is CN as the nucleophile. You end up with, well, not a tertiary alcohol because you started with an aldehyde, but instead of a ketone, but it made an alcohol and also added the leaving group. You can use a Grignard reagent as the nucleophile in lots of reactions. This is our old friend when you do it with an epoxide, and we've seen that one in previous videos. You can also do it with carbon dioxide to create a carboxylic acid. You can do it with an aldehyde to create a secondary alcohol, or you can do it here with an ester, and one equivalent will make that ketone, 2 equivalents will make the tertiary alcohol. So that's 2 equivalents of the Grignard. 13, these are common reducing agents, NABH4, lithium aluminum hydride, and H2PDC. NABH4 is the weakest among them. It doesn't reduce the ester or the double bond, but it does reduce the aldehyde, and it will also reduce ketones if you want it to. Lithium aluminum hydride also reduces the aldehydes and ketones, along with NABH4, but it'll also do this ester. It'll also do carboxylic acids and amides, or cyanos if you happen to see them, though H2, rainy nickel is normally what you'll see reducing a cyano. H2PDC is sort of your all-in-one. It reduces everything. It reduces the carbonyls to alcohols and the double bond to a single bond.